Hello everyone. Today's topic is Chapter 14 Solid Waste. The picture on the left is cars abandoned in Conservation Park, Australia, and the picture on the right is dumpster and recycling containers at Park, Illinois. Environmental engineers design systems to manage solid waste properly and consider the impacts or designs on the end-of-life management options. Common ordinary household and commercial waste, called refuse or municipal solid waste (MSW), is the subject of this chapter. The municipal solid waste problem can be separated into three steps: collection and transportation of household, commercial, and industrial solid waste, recovery of useful fractions from this material, disposal of the residues into the environment. In many locations in the United States and other countries, solid waste from households and commercial establishments is collected by trucks. Sometimes these are open-bed trucks that carry trash or bagged refuse, but more often these vehicles are packers trucks that use hydraulic rams to compact the refuse to reduce its volume and make it possible for the truck to carry larger loads. Figure 14.1. Commercial and industrial collections are facilitated by the use of containers, dumpsters, or roll-offs that are either emptied into the truck by using a hydraulic mechanism or carried by the truck to the disposal site. Figure 14.2. Vehicles for collecting separated materials, such as newspaper, aluminum cans, and glass bottles, are also used. Figure 14.3. Various modifications to this collection method have been implemented to cut collection costs and reduce accidents, including the use of compactors and garbage grinders in the kitchen and semi-automated and fully automated collection. The householder is given a large plastic can, often 24036OL, and is asked to roll the can to the curb every week for collection. The truck is equipped with a hydraulic lift or mechanical arm that empties the can into the truck. Figure 14.4 and Table 14.1. Other alternate systems have been developed for collecting refuse, one especially interesting one being a system of underground pneumatic pipes. In areas with low population density, drop-off, or convenience centers are common. Figure 14.5. The selection of a proper route for collection vehicles, known as route optimization, can result in significant savings to the hauler. The problem of route optimization was first addressed in 1736 by the famous Swiss mathematician Leonhard Euler. Pronounced Euler. He was asked to design a parade route for Königsberg such that the parade would not cross any bridge over the river Pregel more than once and would return to its starting place. Euler's problem is pictured in Figure 14.6. The objective of truck routing is to create an Euler's tour wherein a street is traversed only once and deadheading, traveling twice down the same street, is eliminated. Travel takes place along specific length streets and bridges. In Euler's problem that connect nodes, intersections, and Euler's tour is possible only if the number of links entering all the nodes is even numbered. The nodes in Figure 14.6 bar through D and all of them have an odd number of links, so the parade the king wanted was not possible. Example 14.1 and solution. Common sense routing is sometimes called heuristic routing, which means the same thing. Some sensible rules of thumb, when followed, will go a long way toward producing the best collection solution. For example, 1. Try to avoid heavy traffic. 2. Try to always make right-hand turns. 3. Try to travel in long, straight lines. 4. Try not to leave a one-way street as an exit from a node. Tremendous savings can often be realized by seemingly minor modifications to the collection system because this is usually the greatest cost center for refuse management. There is a point at which the cost for individual collection vehicles to travel directly to the disposal site, known as direct haul, costs more than to use a transfer system. Figure 14.8. A transfer system consists of a transfer station, where waste is consolidated, and transfer vehicles, which are tractor-trailers or rail cars. The transfer vehicles can carry a much larger load than the packer trucks. The flow of materials through the human ecosystem is not unlike the flow of nutrients or energy through natural ecosystems and can be similarly analyzed. Figure 14.9 shows a black box that represents human society, just as we use a black box to represent an ecosystem. In an ecosystem, nutrients are extracted from Earth used by the living organisms and then redeposited on Earth. Similarly, human society uses raw materials extracted from Earth that are manufactured into products to be used by human beings and then discarded. The mass balance shows the flow of materials through this black box. If a raw material, such as iron, is considered at steady state, the amount of iron ore extracted from Earth must equal the amount of iron discarded, as ferrous materials equals a Figure 14.11 is a more detailed representation of materials flow through human society. The width of the bands is intended to indicate the mass rate of flow, e.g., millions of tons per year. The wider the band, the larger the flow. All the materials originate from Earth, and the amount of material extracted is represented in the figure by the letter. The public can exercise three alternate means for getting rid of its unwanted material once it is generated: reuse, recycling, and disposal. Reuse extends the life of the original product, thus reducing waste. Recycling or material recovery, on the other hand, involves the collection of waste and subsequent processing of that waste into new product. As shown in Figure 14.11, material recovery uses domestic waste rather than raw materials as the feedstock. A central processing facility is known as a material recovery facility, or MRF, pronounced MRF. The main feature of material recovery in a MRF is that the recovered materials are produced from mixed or source-separated domestic waste and are then reintroduced into industrial use. The most difficult operation in recycling is the identification and separation of plastics. Because mixed plastic has few economical uses, plastic recycling is economical only if the different types of plastic are separated from each other. The plastics industry has responded by marking most consumer products with a code that identifies the type of plastic, as shown in Figure 14.12. Examples of the uses for the different types of plastic are listed in Table 14.2. Realistically, sometimes finding and reading the code is a challenge, and there is almost no chance that a domestic household will have 7 different waste receptacles for plastics, nor are there enough of these to be economically collected and used. Mechanical recovery operations have a chance of succeeding if the material presented for separation is clearly identified by a code and if the switch is then sensitive to that code. Currently, no such technology exists. In fact, most recovery operations employ pickers, human beings who identify the most readily separable materials, such as corrugated cardboard in HDPE milk bottles, before the refuse is mechanically processed. Many items in refuse are not made of a single material, and to be able to use mechanical separation, these items must be separated into discrete pieces consisting of a single material. One means of producing single material pieces and thereby assisting in the separation process is to decrease the particle size of refuse by grinding up the larger pieces. This will increase the number of particles and achieve many so-called clean or single material particles. The size reduction step, although not strictly material separation, is commonly a second step in a MRF after the picking process. Size reduction is followed by various other processes, such as air classification, which separates the light paper and plastics, and magnetic separation for the iron and steel. Various unit operations used in a typical MRF are shown in Figure 14.13 on the next page. The recovery of materials, although it sounds terribly attractive, is still a marginal option. The most difficult problem faced by engineers designing such facilities is the availability of firm markets for the recovered product. Occasionally, the markets are quite volatile and secondary material prices can fluctuate wildly. One example is the secondary paper market. Paper industry companies are what is known as vertically integrated. This is schematically shown in Figure 14.14. One product that always has a market is energy. Because refuse is about 80% combustible material, it can be burned as is, or it can be processed to produce a refuse-derived fuel, RDF. A cross-section of a typical waste-to-energy facility is shown in Figure 14.15. The refuse is dumped from the collection trucks into a pit to mix and equalize the flow over the 24-hour period, since such facilities must operate around the clock. Because solid waste can be combusted as is, and because it can also be processed in many ways before combustion, there might be confusion as to what exactly is being burned. The American Society for Testing and Materials, ATHM, developed a scheme for classifying solid waste destined for combustion. A particular concern to many people is the production of dioxin in waste combustion. Dioxin is actually a family of organic compounds called polychlorinated dibenzodioxin, PCD. Members of this family are characterized by a triple ring structure of 2 benzene rings connected by a pair of oxygen atoms, Figure 14.17. A related family of organic chemicals are the polychlorinated dibenzofuran, PCDF, which have a similar structure except that the 2 benzene rings are connected by only 1 oxygen. The sites that are used for the attachment of chlorine atoms are identified by number, and the signature identifies the specific form of PCDD or PCDF. The only two realistic options for disposal are in the oceans or other large bodies of water and on land. The former is presently forbidden by federal law in the United States and is similarly illegal in most other developed nations, although the volume of the refuse is reduced by over 90% in WTE facilities. The remaining 10% still has to be disposed of somehow along with the materials cannot be incinerated, such as old refrigerators. The placement of solid waste on land is called a dump in the United States and a tip in Great Britain, as in tipping. The dump is by far the least expensive means of solid waste disposal and thus was the original method of choice for almost all inland communities. Rodents, odor, air pollution, and insects at the dump, however, can result in serious public health and aesthetic problems, and alternate methods for disposal are necessary. Larger communities can afford to use an incinerator for volume reduction, but smaller towns cannot afford such capital investment, so this has led to the development of the sanitary landfill. A sanitary landfill differs markedly from open dumps in that the latter are simply places to dump wastes, while sanitary landfills are engineered operations designed and operated according to accepted standards. The basic principle of a landfill operation is to prepare a site with liners to deter pollution of groundwater, deposit the refuse in the pit, compact it with specially built heavy machinery with huge steel wheels, and cover the material at the conclusion of each day's operation. Figure 14.18. Engineers designing the landfills first estimate the total volume available to them and then estimate the density of the refuse as it is deposited and compacted in the landfill. The density of refuse increases markedly from when it is first generated in the kitchen to when it is finally placed into the landfill. Table 14.3 is a crude estimate of the density of household refuse. Example 14.2 in solution. An added complication in the calculation of landfill volume is the need for the daily cover, which may be removable, such as a plastic tarp, and not use any of the volume, or may not be removable, such as dirt. The more permanent cover material, e.g., dirt, that is placed on the refuse, the less volume there is available for the refuse itself, so the shorter the life of the landfill. Commonly, engineers estimate that the volume occupied by covered dirt is 1/4 the total landfill volume. However, sanitary landfills are not inert. The buried organic material decomposes, first aerobically and then anaerobically. The anaerobic degradation produces various gases such as methane and carbon dioxide and liquids known as leachate that have extremely high pollutional capacity when they enter the groundwater. Liners made of either impervious clay or synthetic materials, such as plastic, are used to try to prevent the movement of leachate into the groundwater. Figure 14.19 shows how a synthetic landfill liner is installed in a prepared pit. Synthetic landfill liners are useful in capturing most of the leachate, but they cannot be perfect. Wells have to be drilled around the landfill to check for groundwater contamination from leaking liners, and if such contamination is found, remedial action is necessary. Modern landfills also require the gases to be collected and either burned or vented to the atmosphere. The gases are about 50% carbon dioxide and 50% methane, both of which are greenhouse gases. In the past, when gas control in landfills was not practiced, the gases were known to cause problems with odor, soil productivity, and even explosions. Now the larger landfills use the gases for running turbines to produce electricity to sell to the power company. There is a third way we can affect the quantity and content of the solid waste stream. Carefully select the materials and products we use and hence have to throw away. The question, of course, is why should we? Consider the utility of a person rejecting an unnecessary bag at a store. The effort may be significant, you sometimes have to argue, and the convenience is less because now the purchase is not carried as conveniently. What then is the benefit to you to reject the bag? Essentially none at all. Why ought you to do something that is not to your measurable benefit? The answer might be that it is the right thing to do, and this may be perfectly satisfying to you. One means of getting a handle on questions of material and product use is to conduct what is known as a life cycle analysis (LCA). Such an analysis is a holistic approach to pollution prevention by analyzing the entire life cycle of a product, process, or activity encompassing raw materials, manufacturing, transportation, distribution, use, maintenance, recycling, and final disposal. LCAs are performed for several reasons, including the comparison of products for purchasing and the comparison of products by industry. One problem with such studies is that they are often conducted by industry groups or individual corporations, and surprise, the results often promote their own product. LCAs also suffer from a dearth of data. Some of the information critical to the calculations is virtually impossible to obtain. The simple example of the difficulties in LCAs and finding the solution to the great coffee cup debate, whether to use paper coffee cups or polystyrene coffee cups. The answer most people would give is not to use either, but instead to rely on the permanent mug. But there nevertheless are times when disposable cups are necessary, e.g. in hospitals, and a decision must be made as to which type to choose. So let's use LCA to make a decision. The EPA developed a national strategy for the management of solid waste called Integrated Solid Waste Management, ISWAM. The intent of this plan is to assist local communities in their decision-making by encouraging strategies that are the most environmentally acceptable but providing flexibility to manage wastes efficiently. It is based on the solid waste management hierarchy, with the most least desirable solid waste management strategies being source reduction, recycling, combustion, landfilling. That is, when an ISWM plan is implemented for a community, the first means of attacking the problem should be by source reduction. At a household level, it is possible through judicious buying to significantly reduce the amount of waste generated in each household. For example, buying produce unwrapped instead of on plastic trays with shrink wrap is one simple way of reducing waste. Purchasing products that have a longer life is a second way of achieving waste reduction. Unfortunately, it's difficult to measure residential source reduction, and you don't need any new equipment to implement it, so it is often ignored. Instead, the focus has been on recycling. The second option, even though an ISWM recycling and reuse should be undertaken after most of the waste reduction options have been implemented because there are costs associated with collecting and processing the recyclable material. Recycling and reuse do, however, reduce some waste. Figure 14.11 is useful in showing this effect. The third level of the ISWM plan is solid waste combustion, which really should mean all methods of treatment. The idea is to take the solid waste stream and to transform it into a non-polluting product. This may be by combustion, but other thermal and chemical treatment methods may eventually prove just as effective. Finally, if all of the above techniques have been implemented and or considered and there is still waste left over, which there will be, the final solution is landfilling. There really is no alternative to landfilling except disposal in deep water, which is now illegal, and therefore every community must develop some landfilling alternative.